Good morning. Here are yet again from another lovely session of CENG 3325 Structural Analysis. Today we're going to be looking at the method of virtual work for beams. So we're going to be looking at virtual work for beams. So this is going to be a continuation of what we looked at, or at least a continuation of the theory that we looked at last time in the last two lectures when dealing with virtual work for trusses. So recall that when we were dealing with trusses, we had this general relationship here. For trusses, we use the following formula. 1 times delta is equal to the summation of FIV times FI L over AE. And this is where our FIV, these are our internal member forces caused by our virtual load. The F internal is the real member forces, member length, area, and cross-sectional area, and modulus of elasticity. Or more generally, this was actually a specific derivation of the more general case for virtual work, where 1 times delta is equal to the summation of FIV times lowercase delta. Where, or if I want to think of this in even more general terms, I could say this is equal to unit virtual load, times our real deflection is equal to the summation of the virtual internal forces times the real member deformation. The real member deformation. And, another way to think of this is the, again, this is our unit load. It would be a 1 kip load, a 1 pound load, a 1 kilonewton load, depending what kind of unit system you have, times the real deflection. That's the actual deflection. This is what we're ultimately trying to solve for. And this is equal to the summation of the forces, the internal forces produced by that unit virtual load, and then times the real member deformation. Or we can also think of this as the virtual external work is equal to the virtual internal work. The virtual external work is equal to the virtual internal work. So we're going to take this unit virtual load and carry it to the real deflection, and then that means that that's the work that will be on the outside of the structure. Then on the inside of the structure, we'll have the virtual member forces, and they'll be going through whatever real deformation the structure is experiencing. So this is, we already constructed this for trusses, but we need to build something like this for beams, or we need to find the equivalent formula. We need to find the equivalent formula or method for beams. And they're definitely going to be different because beams and trusses are, well, fundamentally different. Trusses, of course, are made of only, an ideal truss is made of all pin members. All the members are carrying only axial force. These are going to be very different systems. Although, as we will see, we can use the very similar principle of virtual external work is equal to virtual internal work. So in order to do this, I want to define a virtual system. So consider a beam. First I'm going to define a beam that we're going to be looking at. So consider the following beam. So I'm going to look at a simply supported beam. And this is just going to be a qualitative problem. So a nice simply supported beam. Let's say this thing is length L. So we have a beam of length L. And applied to this is some general loading. So I just have some arbitrary general loading. That's not just my poor drawing skills. I am purposely drawing that as a wavy line to indicate that this is just some general loading case. Although sometimes with the way my drawings look, you wouldn't be able to tell the difference. So this will be W of x here. Again, just our generic loading. And let me call this end A and end B. So let's say we have end A and end B. And let's say I want to find two things. I want to find, let's say I have point C and point D. I want to find deflection at C and rotation at D. So I want to find the deflection at C and the rotation at D. So here, let me show the deflected shape of this. Under this load, of course the actual deflected shape will depend on what kind of loading we have, but the deflected shape is going to look something like this. Something of that nature there. And in terms of our deflection, what I'm really looking for at joint C, I'm looking for this delta here. I'm looking for the change in height of the beam. And when I say the rotation at D, what I'm looking for is basically the slope of the beam. You may recall this from our previous derivations of deflection formulas. And this would be our theta here. So that's going to be our theta. All right, so I'm going to look at a derivation, one for a method for finding deflection and another for finding rotation. So first we're going to look at deflection. So first let us consider deflection. Oh, and also I will indicate that we have a little dx here. This is going to be solved by integration. A truss we use summation because they're individual members, each carrying a single member force. But with a beam, we're going to use a dx, a differential element x, and that dx will be at position at coordinate x. So we are going to integrate our way across the beam, so we'll have a differential element dx, a distance x from the 0 side. Again, though, first let us consider deformation or deflection. Let us consider deflection delta. So as we saw previously, as we saw last time, if we are going to solve for the deflection in something, the real deflection, what do we need to define first? What do we need to define? We have a real system, and then what else do we have? We have a virtual system. Yes, we need to define a virtual system. So we will define a virtual system. And this virtual system is going to be very similar to our virtual system for trusses. So in the trusses, if I want to find the vertical deformation on a joint, I apply a unit downward or a unit vertical load at that joint. So so in this system, we're going to do the same thing. I'm going to remove the real loads from the truss, and I'm going to apply a virtual load at joint C because that's the location I happen to be interested in. So our virtual system here, at location C, I am going to have a 1 kip load, or just a load of 1. You can think of this as 1 kip, but I suppose I should do this unitless. But again, the units of your unit load need to match whatever unit system you're using. If your modulus elasticity is in KSI, then you need to use kips. If your modulus elasticity is in gigapascals, then you'd want to use giganewtons or convert everything to newtons or whatever it might be. The key is that you just simply must use consistent units. So, in turn, we're also going to have member, let me label a few other things. We're going to have member end A and B. That's not going to change. This thing will be length L. And we will be integrating across the beam with a dx located a distance x from the far left-hand side. So distance x and differential element dx. Questions so far? Okay, again, hopefully this is fairly straightforward. Nothing really earth-shattering or innovative here. So, bringing this back to our principle of virtual work, our principle of virtual work is as follows. Our virtual work principle, again, is the virtual external work is equal to the virtual internal work. Virtual external work is equal to virtual internal work, if I can manage not to get tongue-tied. And so, in other words, our one kip or unit load, will move through a real displacement delta. Through a real displacement, or in other words, our unit virtual load, through a real displacement delta. So we already have the left-hand side of this equation. The work virtual external is simply going to be equal to 1 times delta. So we already have the right-hand side of our equation. The virtual external work is going to be equal to the real deformation or the real deflection at that point times our force from our unit load. And we have a force, we have a distance, put them together, we have a work or an energy term. So next, now I need to obtain an expression for the internal work. I now need to obtain some sort of expression for the internal work. So to do this, I think I'm going to do this on the next slide. I want to give myself a little more room for this. Now let's consider the internal virtual work. And so I'm going to look at a differential element. I'm going to look at that dx. Consider differential element dx. So we have this little slice of a beam. We have this small slice of a beam. And it has width dx. And when it's under the virtual loading, it's going to have a virtual moment applied to it. So it has mv, a virtual moment applied to both sides of it. But again, we're dealing with a case where we have a virtual load but a real deformation. So remember that, we're always combining a virtual load with a real deformation. So this MV, this is basically our virtual internal load, but we want to take that through a real internal deformation. And so how do we find the real internal deformation? If you remember back to our beam theory discussions, if our neutral axis is here, and if we look at this in terms of a rotation and a theta, this thing is, as it bends, it's going to rotate, and there's going to be an angle associated with that, with the curvature of the beam, and this is a d theta. So if we have a dx, we have a d theta, and this d theta, if you remember back to our equations of beams and such, we know that d theta is equal to m over ei dx. D theta is equal to m over ei dx. So this is how we can relate and so backing up, m over ei, this is our real load. This is our real internal load. So M is going to be our real internal load, and combining that with EI, we have our real deformation. So again, we're going to get, by putting in the actual real internal moment, dividing by EI and getting a dx and multiplying by dx, we have our real angular deformation, and that's going to be combined with a virtual internal loading. So again, we keep coming back to this. We're combining virtual loading with real deformation. Virtual loading with real deformation. So d theta equals m over EI dx. Again, I want to keep reiterating this because there's going to be more than one m on the board here. So this is m from real loading causing the rotation. From the real loading causing rotation theta, or d theta. Causing the rotation d theta. And so, now, here's the thing. I have a d theta, and I have an m, but what I really want is some expression for work. So how can I get that? Well, I can actually say that dVi, or dWVi, the differential of the internal work, is equal to mv d theta. mv d theta. mv d theta. So, and what are these? Well, mv again. Yes. A question, sir?
That mv, is that the moment of the virtual?
Yes, exactly. mv is the moment caused by the external, I should back up and say this is the internal moment caused by the virtual loading, by the unit virtual loading. But good question. By the unit virtual loading. And again, d theta is rotation caused by real loads. So the question is, how did I get that work equals a d theta? Where did this come from? Where does this come from? How do I end up with a d theta? So if you think of this, you might at first ask yourself, wait, how does this work? How can isn't work a force times a distance? Doesn't that make sense? Work is a force times distance, but I have an angle here. So how can an angle equal a distance? Well, if you assume small angles, if you remember back to your trigonometry, or calculus, or whatever it might be, if we assume small angles, a d theta can be a distance. A d theta can be very similar to a change in distance. Equivalent to a change in distance. Or if you want to look at it from the point of view of, if you want to consider it from the point of view of units, what are the units for moment? The units for moment are basically the same as the units for energy. They are a distance and a force. So in terms of units, it does make sense that we have d theta radians. That's fundamentally a unitless thing. So we can get a work just by multiplying our mv times our d theta. But we're still not done yet. I'm going to take this and plug it into here. So now when I do that, I will have dWVi is equal to mv times m over EI dx. M over EI dx. I'm getting rid of that d theta and putting in something more useful, which is a dx. Now we'll integrate both sides. And I will end up with this here. I will end up with our final expression for the virtual internal work for beams, at least for deflection. So the virtual internal work is going to be equal to the integral from 0 to L of mv times m over EI dx. And that's our virtual internal work. And then combining these two together, since we know that the virtual external work is equal to the virtual internal work, we can just say that 1 times delta is equal to the integral from 0 to L of mv m over EI dx. Over EI dx. And this is something we can actually use. So let me just restate some of these things. Delta, again, is our real deformation. 1 is our unit load. Delta is our real displacement. MV is the internal moment caused by the virtual load. I should probably say unit virtual load here. MV is the internal moment caused by the virtual load. And M is the internal moment caused by the real load. And at this point, if you don't know what E and I are, you may be in the wrong class. So, yeah. All right, so that's that there, or that's our expression for our virtual work. Again, what we're going to do is we can set up a, again, just like we did with trusses, we will apply a unit load where we're interested in finding the deflection, and then we can find our virtual internal or virtual external work very simply. We find the internal bending moment caused by that virtual load, we find the internal bending moment caused by the real load, and combined together we go and find the, we can combine these together to find our full expression here for energy, divide that by 1, and we will have our full delta. Okay, so now let us consider rotation. So remember how I discussed back here, I mentioned that I wanted to look at 2 different cases. One, finding the deflection, the actual vertical distance up and down a beam moves, and the other is rotation, or theta. Now, thankfully, this isn't that much more difficult than finding deflection. It's just, in fact, the right-hand side is actually completely the same. The only thing that's different is the left-hand side a little bit and how you find this. So, but we're going to need a new virtual system for this, though. Now, let us consider rotation. So we're going to need a different virtual system for this. So here, the virtual system, again, define the rotation at D, at point D, at some point D. So I'm going to apply a unit load. Well, let me just draw the beam again. Here's our virtual system. We're going to have the same dx, that's not going to change, and distance x. And length L. And length L. And ends A and B. Now, here is the question. Here's the question I have for you. When we wanted to find a deflection, we applied a unit virtual load. If we're looking for rotation, what do you think? Do you think we're still going to use a load there?
Probably not.
No. What else? What might we use instead of a load? A moment. Yes, exactly. We're going to be applying a couple. So instead of applying a unit virtual point load, we're going to apply a virtual couple, but still a unit couple at that location. So if this is point D that we're interested in, if we have point D, I'm going to apply a unit couple, and that could be a 1 kip foot, a 1 kip inch. Actually, if you're doing this in KSI and inches squared, you would probably want to use the kip inch couple rather than a kip foot couple. Or you could also have, I don't know, Newton meters, kilonewton meters, really just whatever unit system you're working with. So whatever unit system you're working with, you'll have a different unit couple on here. The key, of course, is that it has both a distance and a force baked into it. So, and at first this seems like a real headache, but this really isn't too bad.
Should we assume positive?
Oh, okay. So here's the question. The question was, should we assume positive? Well, in terms of this, basically in terms of the direction we're going to assume, we can just go ahead and assume positive, and whatever direction we assume, that is the, so basically if I think of a couple like this, if I apply a couple to a beam like this, I imagine this thing bending down like this. I imagine torquing that beam and bending it down like this. And so yeah, it's perfectly fine just to assume positive initially. And if we get a negative value, that doesn't mean the deflection, the curvature is necessarily negative. What it means is the curvature is opposite whatever we originally assumed. So in the previous problem on lecture 17, where I went and worked through all of our, that long form example on trusses, I actually ended up getting a negative value for my final deflection. That didn't mean that the deflection was actually in the downward direction. It meant that the deflection was opposite the direction I originally assumed. Originally, I'd assumed a downward deflection in that joint. It turned out it was actually upward because of the way I had that truss supported and designed and such. So that I initially assumed it was deflecting downward. I got a negative. That didn't mean I got everything wrong. It just meant that it was actually going the opposite direction. So same thing here. So you can assume positive, and if you get a negative value, that just means it's deflecting or curving in the opposite direction. So our virtual external work here is just going to be equal to 1 times theta, our actual rotation that we're looking at. And again, this is assuming small angles. Or in other words, change in angle is approximately equal to change in arc length. Or you can think of it as just, you can also just think of it as there is an expression for the work that's caused by a moment is really just it really is just the moment times the change in angle. So in turn, our internal work, however, is going to be exactly the same. So the only thing that's going to change is the right-hand side of this equation. So the virtual internal work is just the same as it was before, the integral from 0 to L of mv m divided by EI dx. The only difference is our virtual internal moment here is going to be driven by this couple rather than being driven by a point load. So what you would do is you'd find the moment function for that, and that would produce your mv there. Really no different than what we looked at for deflection. So our final expression for virtual work for rotation, 1 times our theta, that's what we're solving for again, 1 times our rotation theta is equal to the integral from 0 to L of mv m over EI dx. Over EI dx. And this is our final formula. So we have our formulas now, and what I would like to go through is just a formal listing of the series of steps to how to actually use all this. So I know when you first see these formulas, it can be a bit confusing. So I wanted to work through I'm not going to work through a full example right now, I'll save that for a later video, but I did want to go through a series of steps showing how you actually handle these. Like, I want to provide you the general procedure for analysis. So questions so far? Oh, yes.
Can you repeat why we apply a couple to ID?
Okay, the question was, can we repeat why we apply a couple at D? Yes, because remember, the principle of virtual work fundamentally is that the internal work done by the virtual force is equal to the internal work done by it is equal to the external work done by it, or in other words, a virtual force moving through a real deformation is equal to a virtual internal force moving through the internal deformation. That's the fundamental principle. So we need to have some sort of internal force, we need to have some sort of virtual force that corresponds to the type of deformation we're looking at. We're in this particular example, or this particular instance, we're wanting to find a rotation. And so back here, when we were looking at when we were trying to find a vertical deflection, it made sense to apply a point load downward, a actual load. Here, because we wanted to find the deflection, which is a vertical distance. Here, we're looking to find rotation. We're looking for the angle theta. We're not looking for a distance in the y direction. We're looking for a rotation. And so instead of applying a deflection, a point load downward, we're applying a couple. Does that make sense? Because basically, if you're looking for something linear, you apply something linear. If you're looking for something rotational, you apply something rotational. Does that make sense? Okay, thank you. Okay, so, but good question. So let us consider the general procedure here. So first of all, we're going to analyze the real system. We're going to analyze our real system. So this consists of the beam with the actual real loads on it. So draw the real load diagram. Draw the real load diagram and get equation of bending moment as a function of x. In other words, I'm going to need some m as a function of x. And these can be piecewise functions. And I'm going to talk about that in step 3 of our procedure here. 2, virtual system. So analyze your virtual system. A, if deflection is to be determined, is to be found or determined, apply a unit load at the location where deflection is desired. Where deflection is desired, and B, if rotation is desired, apply a couple at this location. Apply a couple where the rotation is desired. A unit couple at the location where rotation is desired. Where rotation is desired. And regardless of whether you're in case A or B, you get your mv of x function. You get your virtual moment as a function of x. So the next step, I'm going to write on the next slide because it's kind of a longer one. And I'll give a brief sort of mini example of how to handle this. I want to talk about how you handle conflicting zones of analysis. So basically, we'll need to figure out our combined zones of analysis here. We need, because sometimes they'll overlap and we can get some really tricky situations. So I want to find, step 3, figure out zones of analysis. Zones of analysis. So here, example. So what I'm really saying, when I'm saying figure out the zones of analysis, what I'm really getting at is oftentimes, as we've seen previously, you'll have to divide a beam up into multiple zones of analysis as you're integrating across it. But here's the problem. Sometimes the boundaries of discontinuities of your real system don't match up with the discontinuities of your virtual system. So how do you handle that? So your boundaries, you're always going to have discontinuity where you apply that virtual couple or that virtual point load, and that may not match up with the actual discontinuities in your real loading. So consider this. Let's say, for example, we had a beam that was 15 feet long. Let's say we had a beam that was 15 feet long, and when you worked through it and got the real load or the real moment, you would found that m as a function of x equaled m1 of x, some m1 function. So maybe you found this equal to piecewise function, m1 of x when x was between 0 and 15 feet, or 0 and 5 feet, sorry. And you found that it was equal to some other expression, m2 of x, when x was between 5 feet and 10 feet, or sorry, 5 feet and 15 feet. And then for whatever reason, maybe you wanted to find the deflection at at x equals 8 feet or something. Your virtual system, you found that this was equal to mv1 as a function of x when x was between 0 and 8, and mv2 of x, some other expression, when x was between 8 and 15. Do you see the problem here? These don't match up. Our boundaries don't match up. So how can we deal with this? Any idea? Yeah, we basically, we break them into compatible zones. So what I'm going to do is, I'm going to combine these together into 3 combined zones. Into 3 zones. The whole thing is that you're going to have 3 different, when you integrate these, you're going to be integrating the MV and the M together. So it is paramount that you have the same boundaries on each of these zones. So what I'm going to do is, I'm going to break these into 3 zones. For this particular problem, that would be 0 to 5, 0 to 5, and then that would be 5 to 8, and 8 to 15. And then my m function would end up looking like this. M is a function of x. Well, thankfully, I wouldn't even have to rewrite the functions in certain cases. I would just say that m1, we'd have that m1 of x when x was between 0 and 5. 0 feet and 5 feet. m2 of x when x was between 8 feet and 5 feet, or 5 feet, 8 feet, and we just reuse that m2 of x in the region from 8 feet to 15 feet. So really this is the same as this here. And then mv of x, basically I just split this one apart to take into account the break that we would have at this, for the virtual moment. And then mv as a function of x, we do something very similar, except the break would be in the first one. We're going to have mv1 as a function of x when x is between 0 and 5 feet. Then we're going to reuse mv1 of x when x is between 8 and 5 feet. And then we just use mv2 of x in the last region, when x was between 8 feet and 15 feet. And now we have 3 zones of integration that match up nicely, and I can put this one with this one, this one with this one, and this one with this one. So if you go and you find your moment functions and you end up with incompatible boundaries, it's really easy just to break them up as required. Okay, some other things on this. Other notes. Note. Sign convention of m of x and mv of x must be the same. So they must be the same. In other words, they have to have the same positive direction, positive x direction, so like maybe positive to the right, and the same origin. And the same origin point. So again, they have to have the same origin. The x equals 0 has to be x equals 0 for both of them. And finally, there's a step 4 we can look at. Our final step. So again, it is important to keep all of our origins aligned, all our coordinate systems aligned. You can't exactly take an integral with 2 incompatible systems of units, or it's not, I shouldn't say systems of units, systems of, well, for example, if one had x defined as 0 at the middle of the beam for some odd reason, well, I don't know why you would do that, but let's say you did for some reason, well, then you'd have to define the other one that way, or define them both from the left end of the beam, or whatever it might be. Then, step 4, determine the desired rotation or deflection by applying our formulas. By applying, say, 1 times delta is equal to the integral of 0 to L of m, let's say, that would be, m vm over ei dx, or 1 times theta is equal to the integral from 0 to L of mvm over ei dx. And I do want to note something on here. If going back to our example from previously, this may be applied, this integral, and this one as well, may need to be applied across multiple zones. May need to be applied across multiple zones. And I want to illustrate how that would work. And I'm going to use the same 15-foot beam example from before. Over multiple zones. So in the example from the previous slide, thankfully we can just add these together because this is an energy consideration. So we can just add things together. So I would have my 1 times delta at some joint, and this would equal the summation of 3 integrals. The integral from 0 to 5 of, and I'm going to use the terminology that I used before, or the variable names from before, m1 of x, mv1 of x over ei dx, plus the integral of 5 to 8 of, that would have been m2 of x, mv1 of x over ei dx, plus the integral from 8 to 15 of m2 of x, mv2 of x over ei, integrated from 8 to 15 and dx. And as a note here, we do have to watch our units. This is the easiest way to screw something up with this method. Like a lot of things we do in structural analysis, it's very easy to screw up the units. We must watch our units. So if I wanted to use this integral in this exact form, I have my boundaries set up in feet. So if I wanted to keep this integral unchanged, what I would need to do is I would need to convert my E from, say, 29,000 KSI, or from KSI to something in KSF, kips per square foot. And I would need to use, instead of moment of inertia in inches to the fourth, I would need to use moment of inertia in feet to the fourth power. So, or I could convert my bounds into inches or whatever it might be. But the whole thing is we simply must use compatible units. Always and always, we must use compatible units in all cases. Okay? And so finishing up, I'd like to just give some notes on why we might use this. So we have gone through this theory, we've looked at the method, but I would like to sort of bring us back to reality, that now that we've been lost in the weeds for a while of this math, I would like to discuss why would we do this? So what's the purpose of this? So what is the purpose of this? Now, you as students might think the purpose of this is just because I love torturing all of you, but with lots of integrals. But while that may be true slightly, that's not really the point of this. No, the real purpose of the method of virtual work, for example, for beams, is, okay, so backing up, why would I ask what's the purpose of this? Well, I am finding the deflection and the rotation, right? We're finding the deflection and rotation. And though, this is nothing we haven't seen before. Like, we've already learned how to find deflection for beams. So why are we going through all this effort? Why are we going and saying, oh, why are we going through this virtual work stuff? Why are we applying virtual loads? Why not just do a plot? If we have the moment function already, why not just apply 2 other layers of integration and be done with it? So what's the purpose of this? Well, what it really comes down to is the method we've learned previously is limited. Of deflection via direct integration are limited. Are limited. Namely, they can really only be used for statically determinate systems. For statically determinate systems. For statically determinate systems. So they can really only be solved for statically determinate systems, and we don't necessarily have that here. Or we want to be able to work with something where it's not statically determinate. Virtual work is a method that is much more flexible. Is much more flexible. Can be used for statically indeterminate systems. Beams, and can be used for things like thermal expansion stress. Things that aren't even really loads or external loads, like thermal expansion stress. And can be used for things like thermal expansion. All right, so that's what I had to cover on the theory for virtual work for beams. I will put out a later follow-up video covering how to handle this with a long-form example. But this is the theory, and this should serve as an excellent introduction to working through virtual work with beams. That'll do it for today. Thank you for watching, thank you for participating, and as always, thank you.